Hello everybody, my name is Ashrit from CSE AML A section. So today I'm going to be talking about for my tech talk topic is the Bernoullis equation and theorem. It's an like use case of the Bernoullis equation studied. So in this PPT we're going to be exploring about the fundamental principles of Bernoullis equation, about Bernoullis theorem, and talking about the complexities of fluid dynamics, of how it is and all. So overall, we're going to go about how these both are like an extension of what we studied in class and as such. So that. So while we come to the father of fluid dynamics, Daniel Bernoulli. So when we talk about him, he is a Swiss scientist. Daniel Bernoulli was a Swiss mathematician and physicist who made significant contributions to fluid mechanics or fluid dynamics. He published his groundbreaking work, Fluid Dynamica. It's another name for like in Swiss dynamics. In 1738, he is the starting pioneer of fluid dynamics. So his research is focused on understanding the fluid, like flow of fluid, including fluid mainly includes gases and water, like liquids. So his work laid the foundation for modern day fluid mechanics or fluid dynamics. So if not for him, you wouldn't be able to use this as such. So the core concept of fluid dynamics or pressure, velocity, and height relation. What is the relation between these three? So while we talk about in the case of the fluid dynamics, fluid mechanics, Bernoulli's equation states that the total mechanical energy of a fluid is constant along a streamline fluid. In the streamline flow, where the flow doesn't have any disruptions, the total mechanical energy is constant. So this energy is comprised of three main components: the pressure energy, the energy for exerted on like a liquid, and the energy because of that, the kinetic energy because of the flow, the potential energy for the dormant atoms, the dormant particles. So these individual needs individual calculations as well. So the energy, total energy comprises of these three components. And the equation demonstrates the inverse relation between the pressure and velocity, meaning when velocity increases, the pressure decreases, and vice versa. When the pressure increases, the velocity decreases. So it can be taken into both accounts as well. So that. And while we talk about deriving Bernoulli's equation, like a step-by-step equation, explanation of how we'll do that right now. So how he derived it and what principles he used in that as well. So the main principle, let me start off while talking about the equation, is conservation of energy. As we talked about in a streamlined flow, the total energy is constant. It don't change. So the derivation begins with the principle of conservation of energy, which states that energy cannot be created nor destroyed. Energy cannot be created nor destroyed. It can only change between form. So the laminar flow energy, or the pressure energy, potential energy, kinetic energy can be converted into other forms. That is it. And the another principle we can talk about here is the Newton's second law. Like it then applies Newton's second law of motion to a fluid element relating force to mass and acceleration. Newton's second law is force equal to mass and acceleration. So using conservation energy as a basis and using Newton's second law to move forward on like the explanation or how he derived the equation. So we can understand he used these two principles in this case. And while we talk about Bernoulli's theorem, conservation of energy in fluid flow. So we've talked about in a fluid flow, in a streamlined flow, energy is always constant. So in the Bernoulli's theorem states that total energy of fluid along a streamline remains constant. Hence, we use conservation of energy, like we discussed in the previous slide. Conservation of energy plays a big part in this theorem. And while we talk about the pressure velocity trade-off, the theorem implies that as the velocity of fluid increases, the pressure decreases, and vice versa. Spoken of this point before as well. We've got to know the relation between the pressure and velocity and how each one differs between each as well, how it's related, the inverse relation of it as well. And when one increases, the other decreases. When the other decreases, the another one increases. So we've got to know about that relation. And as such, again, we've discussed the constant energy and where it's used as well, streamline for the flow and all. So let's talk about the assumptions and like the limitations and where specifically it needs to be applied, the rules that it's in place. So incompressible fluids, fluids that must be incompressible, meaning the density remains constant. The linear density, density along 1 unit square cannot be decreased or increased. It needs to be fixed about a point. So that steady fluid flow. Flow must be steady, meaning the velocity and pressure do not change over time. It needs to be constant throughout. So that the like the laminar flow when we talk about over here specifically, and the no viscosity. Viscosity must be negligible and meaning no internal friction is minimal. So viscosity is basically fluid flow in layers. So the frictional force between two layers is known as viscosity. In other words, viscosity can be told as how thick it is. The thickness or like how thick the fluid is referred to as how it's viscous or not. That so these are some points that are like needed to imply or to use Bernoullis theorem and equation. Let's talk about the real world applications. So where this specifically is used in our modern day-to-day life. So from aeroplanes to pipelines, as you know, fluids refers to both liquids and gases. So airplane wings are designed in such a way, are created a pressure difference resulting in lift. So when the flow is like how it's like this, to suppose the airplane's wing, it creates a zone of higher pressure and lower pressure on top. That is why it causes us to lift like this, pushes up. So the change in pressure causes the airplane to lift off, as we call it. So that's that. So venturimeter is another thing we use. I used to measure fluid flow velocity by applying Bernoulli's principle to a constricted area about a singular area when you use Bernoulli's equation. And prime example for that is the venturimeter. And the wind turbines generate power by converting kinetic energy from wind to mechanical energy. So wind energy, when we talk about as such, is another key thing that you use in day-to-day life. And also, when it comes to pipelines, it uses Bernoulli's equation, Bernoulli's theorem, like similar to the venturimeter about a unit area. So, example problems like how we're able to identify calculating fluid velocity using Bernoulli's principle as such. The identify known variables start by identifying the values such as pressure, height, density, flow rate, and different other things as well. So and then apply Bernoulli's equation. Substitute the known values into Bernoulli's equation to find out unknown velocity. So to find the unknowns is our main principle. So to if they ask us to find for velocity, is to simplify the equation to solve for velocity of the fluid at like a desired location. And so with this, you'll be able to find out the things that's required for you as well. So common misconception when we talk about the myths about Bernoulli's equation theorem. Curved surfaces, the pressure difference on curved surfaces is primarily driven by the Canada effect and not Bernoulli's principle. So that is another thing. The fluid flow. It's important to understand that Bernoulli's principle applied to fluid flow along streamline and not across surfaces. The air pressure, again, when we talk about Bernoulli's equation does not directly explain why things flow, but it contributes to the lift generation. So when we talk about that is another important factor. Summary and key takeaways. So mastering Bernoulli's equation, energy conservation, Bernoulli's principle is based on the principle of energy conservation, as we talked about. Pressure pressure velocity trade-off. So when one increases, the other decreases. The practical application. Bernoullis principle have a wide range of application in various fields. So with this, I would like to conclude that Bernoullis equation, Bernoullis theorem is key and important factor in our day-to-day life as well. So how it is used and all is these is what are the points I would like to summarize. Thank you.